Obrigado. Hello, everybody. Good afternoon. Today, it's what I will call here as payday. I have a debt with you because I was asking you to apply the charity principles to hold your anxiety with respect to the use of the second order approximation, which was used, in fact, in all the preceding approach to the derivation of the Schrödinger equation. We have done the first derivation in terms of the characteristic function, and we have used for the first time this approximation. At least at this point, we will be calling it an approximation. And then we have done a derivation based on different axioms, but also using the second order approach. After that, with respect to the first derivation, the derivation based on the characteristic function, we have shown that the Feynman's derivation of quantum mechanics, or the Schrödinger equation, is also based on a sort of an infinitesimal parameter, which is time, in his theory. We passed from through the derivation based on the entropy, as I have said. We then showed that the stochastic derivation of de la Peña and Seto gives also the Schrödinger equation, and they also use the notion of a second order expansion. And I was, for the time being, I have to assume that this is an approximation. In some sense, this should be considered an approximation because I am, of course, using an expansion that goes only up to second order terms. But I will show you in this presentation that if you assume the central limit theorem to apply, the second order expansion is no approximation whatsoever. It's in fact the exact result, and it is the very result of the central limit derivation. In fact, I will show you that if you assume the central limit theorem and the Liouville equation, which of course is the physical part of the problem, you can derive the Schrödinger equation in quite the same ways that we have done so far. Okay, so let me state the problem again. And the problem was the following. What does it mean to have infinitesimal displacements delta x? Should they be really infinitesimal after all? Because we were using an expansion up to second order in delta x, and we assumed that this means that this parameter of the expansion is infinitesimal. But must we assume that? It is necessary to assume that. Okay, this gives us a strange result. I have already said that because I got the phase space probability density function by the inversion of the characteristic function. And if I'm inverting the characteristic function, of course, the inversion is related to this parameter. And so I have to integrate in this parameter from minus infinity to infinity, which means that in our case, we are assuming, in fact, that delta x or delta q, doesn't matter, is something varying in the whole interval of the real numbers. So it, of course, cannot be infinitesimal. As I have said, this was explicitly used in the entropy derivation, but it is within all the derivations that I have made so far. Okay, so what we want to know here? We want to know first, of course, if this delta Q must be infinitesimal. But when we will look at the answer for this problem, we will find the interpretation of this delta Q, okay? And of course, if we can connect quantum mechanics with the central limit theorem, we will know more about what quantum mechanics is really about. Okay, so we may write here the usual expression that you may find in the literature. For instance, this one is, you may find it in the book of Kinchin. I don't know if the name is correct here, but the pronunciation is correct. And you may, of course, find the probability density function with respect to the derivatives of the characteristic function. And this is exactly what we have found. So this makes us hypothesize that our results have something to do with the central limit theorem. And this is our justification to try to make this connection. Okay, these are the symbols, the statistical elements that appear in the probability density function. We have already seen that in our derivations, almost all of them. Okay, so let us see what the central limit theorem is saying. I will, of course, work with the central limit theorem in one dimension. We are, of course, using it in two dimensions if we are assuming a one-particle physical system, because we are developing our results with respect to the phase space. But let us see if we assume one dimension, it will be enough for us to understand what is really going on here. So the theorem is just that. Consider a number n of random variables. They are independent random variables. This is very important. And this is the first imposition of the theorem. With the averages for each random variable, each random variable has associated to it a probability distribution. And when we average this random variable with respect to this distribution, we get the average for the random variable, which is given here for the same index, and also its variance, again, with the same index here. So we need not to have the probability densities Fi all equal to one another. We may have different probability distribution functions, and still the final probability distribution function for this variable, which is the sum of random variables. This is extremely important. Will give the function that we are trying to find. So if we put this sum y as the sum of these random variables, then under very general conditions, the reduced variable, this is just a mathematical step to get the Gaussian at the end, as what we usually call the normal 0, 1, which is 0 average, because you have changed the average here, and 1 dispersion equal to 1, which is the dispersion is given by this term here. So in this case, the average of the whole process is just the sum of the averages, and the variance of the whole average is the sum of the variances, the individual variances. And we may see that, may prove that the resulting distribution for this variable is just a Gaussian distribution with an average 0, as I said, and a variance equal to 1, as I also said. So the distribution probability function of the random variable y will be just a Gaussian function given in these terms here, okay? If, of course, you take the limit, and this is extremely important for us, the limit that n goes to infinity. That is, if you sum an infinite number of random variables, okay? Okay, this is the central limit theorem. It is a very general theorem of statistics, and also very used in statistical mechanics, mainly with respect to the random walk problem. Okay, so let's try to demonstrate this theorem. I will give you a sketchy demonstration because it's important to understand the meaning of the terms that appear in the process of the derivation, okay? So let's go to the derivation. Since we are in one dimension, I will assume here 3 different random variables, and I will assume that I want to go from this point to this point by means of a step 1, a step 2, and a step 3. So I may go in a number of different possibilities, okay? But the constraint here is that the space that I cover is only the same space, which is dy. So all the length of this x is just dy, okay? That is the sum of our random variables, can be any. For instance, this sum here in this realization is given by different values for yk, but the result is within this one, and in fact it is equal to this one here when you sum, of course. And the sum again will give all the same results because, as I said, this is just dy. Okay, how can I calculate the probability density function for such displacement here? We are assuming that y means a displacement. It may be displacement on phase space or a displacement on configuration space. We are assuming that it's a displacement on phase space, okay? So this means that we are assuming that here we have the momentum axis, okay? And we are, in fact, in all these approaches here, we are assuming region in the configuration space of size delta Q. Okay, so we now use the fact that the probability density functions for each random variable are independent. So if they are independent, of course, the total probability density function for this path here, from here to here, is just the product of the individual probability density function for each variable of the process. Of course, this process must be handled, but we now are sure that quantum mechanics is related to random behavior, so there is no problem to assume that while we try to make the connection between these and the quantum mechanical realm. Okay, this is a very difficult integral to make because we may have different limits for the integration, because the only thing that we are assuming is that the sum of them gives dy. So to make this easier to calculate, we may use the Dirac delta function, which is here, because the Dirac delta function allows me to use integration limit, the whole space for the integration limits, because I am already assuming that whatever these yk may be, the sum of them must be equal to y, or else this term will give 0, and then the sum will give 0 in any case. So I'm summing only those terms that give this result here for the displacement. Okay. Now I will write these, in this step is very important, because I will write this delta function, this Dirac delta function, in terms of its Fourier representation. So we know that if the delta function, Dirac delta function, is given by this expression, its Fourier representation is just this integral here. If we use that, we can rewrite the expression for the probability density function, and now it will appear. I will make a change in the integration order. Let me show you that. I will make I'm here making the integration over dy, and I'm changing the order of the integration here, and this, of course, is inside this integral here, of course. It's just a way to write it. This is a function of t, okay? But look at this. Look at this. This is, if you want to connect also at this point, this derivation with our derivations, this is the individual characteristic functions for our variable here, which is connected to the single random variable of the sum of random variables. So when we were talking about z in our derivation, we were really talking about this characteristic function for this approach. And look that we are assuming that we have finite dy that is the sum of, in the limit, an infinite number of random variables, which may, of course, be infinitesimal. Because if they were not infinitesimal, of course, we will be getting an infinity delta y. Okay. Okay. So let's go a little bit further. And this is the characteristic function for delta q, of course. And now we may write this expression here in this way. But look that when we do that, the y is just a dummy variable. because of the inversion of the integration. And so what we get here is that the probability density function in terms of y is just the Fourier integral of the characteristic function of the individual elements to the n power. This is very important because this is the connection between the infinitesimal characteristic function and the finite characteristic function, which is given by that. And it's a very useful result of statistics. If you have independent random variables, the characteristic function is just the product of the individual characteristic function, okay? But of course, we have just get the result again. Oh, that is, if we have a process of the type given here in this theorem, we may have infinitesimal displacements, but these displacements, when we assume this situation for n variables, gives this characteristic function for a finite displacement, which is just what we get when we make n goes to infinity. And this is why the central limit theorem is also called an infinitesimal theorem. Okay, so let's continue. We will now make the rescaling of this variable just to get the results the way we want to. This is not really important for the derivation. I should have made the derivation, continue the derivation in these terms without this rescaling, but the rescaling gives us the following result. Well, of course, I jumped here some steps, algebraic steps that are not very difficult in any way to make. In the paper that I published in 2005 in the Foundations of Physics, these steps are done with in a much careful way. Okay, these results very nice, because this result shows the n explicitly. The n appears here in every term of the expansion. The result appears. This will be interesting because we will show, in fact, that even if you keep terms with another greater than 2, here we are getting up to second order. This one is because this one here. You will get 0 because n will make these terms which has this term which have greater dependence with n will go to 0 in the limit of n goes to 0. Let's see how we can manage this expression. It's very quick to do that. We have here this first term minus I roots of square root of n m over s t. Note that this term can cancels with this one. We get in the numerator the root of n, and these will cancel out. This is an average, okay? This is the average. I'm using these letters to simplify matters. And here we have just that. And this cancels with this one. We can continue here. We have then n over 2ns squared m squared plus s squared t squared. Of course, this cancels. And we have this r, which is multiplied by n. We also have this term, but this term is squared. So the first term will give minus, which is now given the square here, m squared n, but this n will cancel with this one here. But let's cancel it here. S squared, t squared. And this term becomes positive because we have here a minus sign. So minus plus. Minus, I will now make the relation between the square of this one. Well, I can continue that, but of course this will give a greater power, but let's continue. I will put another term here, which will be given as the third power, because I can make the product of these two. I'll assume that this is just the third power, which is 1/2 m over the root, the product of these two, n to 3.5, s to the third power, m squared plus s squared, t to the third power, and etc. Okay? We can now connect this term with this one here. The m cancels out. We have the same thing, the same coefficient, the same s squared in the denominator, and then they cancel. And if they cancel out, we can also cancel the numerator with the denominator, and we get just minus 1/2 t squared, plus terms that you can show that goes to n minus alpha when alpha is greater than 0. Okay, so you now have just found that the logarithm of the characteristic function, the rescaled characteristic function, this is why we have a tilde here, is just this term. I will put here an index n to say that this depends on n. And you, of course, may now make the limit. You may make this limit now, or you can wait to make it a little bit after that. But of course, what is important here is that all these terms here, all these terms, which are very complicated, in Kinchin's book, you find some of the expressions for the first terms, and they are very complicated indeed. But the fact, and the important fact, of course, is that they all depend on some power, inverse power of n. So when you make n goes to infinity, what you have? You have a sum of an infinite number of random variables, and giving a finite value for the variable. So these ones must be assumed as going to infinitesimal value, because of course you must sum infinitesimals to get, if you are summing an infinite number of them, to get a finite value. But our central limit theorem is being derived for this variable. Okay. So when you make this limit here, you get just by inversion. Now you may invert the function, because when you make the limit with n going to infinity, this term, in fact, terms here cancel, go to 0. And when you invert this by the inversion of the Fourier transform, which is our inversion, in fact, it will give just the result that we have obtained. Of course, this result gives the previous result if we assume that our U is just the P. Here it should be T, if our T is big. Okay. This is the derivation. This point is the derivation of the central limit theorem. If we would make the derivation for our problem, we may say that, and this will be important for the next class, we may say that on the phase space, to make such a derivation is to make make a slice here in the configuration space and some random variables in this way. Okay. Well, okay. So let's continue and let's make the connection with our previous derivation. I think the connections are somewhat visible, but not almost. They are almost explicit, but not fully explicit. Let's make them explicit now. So let's come back to the characteristic function derivation, but now let's assume that we may have two characteristic functions to use. We may have an infinitesimal characteristic function, which was the one we used in the derivation, the characteristic function derivation of the Schrödinger equation. And now we must assume that we may have also a finite characteristic function. Of course, we are assuming infinitesimal and finite depending on the parameter delta Q, the small cap delta Q, and lower cap delta Q, and the high cap delta Q. Okay, in this case, this one is infinitesimal. This case, the delta Q is finite, and they are related by this relation here. Delta Q is just n delta Q. I am assuming that each random variable has the same size, but only for the argument of this, for the sake of the argument. But the important result here is that the final characteristic function is the product of the infinitesimal characteristic functions. So in a sense, we may say that if this approach for infinitesimal delta Q is sound, because of the central limit theorem, if we assume the central limit theorem applies in the realm of quantum mechanics, this one should be adequate too. And this one is related to a finite delta Q. But if this delta Q is finite, should we still go only to second order? Yes, of course, this is because just what we have just derived. We know that even these being finite, the central limit theorem, if it applies, it assumes that this characteristic function should be expanded only up to second order. Okay, so there is no inconsistency in the demonstrations, because in fact what we were doing without notice when we derived the Schrödinger equation using the characteristic function, we are in fact using this function, but thinking that we were using this one. This is, I will take the liberty to say something of a personal recollection, my recollections of the time that I was chasing these results, and I really passed very difficult times from 1999 to the year of 2005, because I had done in 1999 the derivation using this notion, because I was unable to explain for the finite delta Q because of the expansion, of course. But of course, I was aware of this problem, the problem that drives us this class, since 1999. And I was sure that the solution of this conundrum, which is a conundrum, will reveal some deep element of quantum mechanics that I was unaware of. And this deep element of quantum mechanics that I was, and everyone was unaware of, was just the connection between quantum mechanics and the central limit theorem. And the impositions, the mathematical imposition of the central limit theorem. And in fact, the central limit theorem gives us more information about our quantum mechanical system, because now, of course, if we assume the soundness of such an approach, we are portraying the quantum mechanical situation for any quantum mechanical system as related to sums of infinitesimal random variables. And this is very important for what we will be saying tomorrow, that is indeed connected to the sum of random variables. And the demonstration that I will present tomorrow, which is the Langevin demonstration, when I will show you that the quantum mechanics can be connected to a Langevin equation, which would be under the Schrödinger equation. The Schrödinger equation will be some sort of f of average of this Langevin equation, or at least the limit of when this system governed by the Langevin equation is left to make its dynamical evolution. And at the end, when you see what you get is the Schrödinger equation, which I will show that must be assumed as a mean value field theory. Okay, so I just want to say that these were very difficult intellectual times for me. I was in much distress between these 5 years, almost all 5 years. But when I get into the demonstration of the characteristic function of the central limit theorem, most of my fears with respect to what I was doing were gone away. Okay, so I have already told that. And what we finally comprehend, or we finally understand, is that the derivation, in fact, is related to this function. And despite the fact that this element can be finite, we can still develop the expression of the characteristic function in terms of this parameter up to second order. And of course, this is in fact the content of the central limit theorem. We can invert without any fear the expression for z. We have done that, and find the probability density function upon phase space. We may have done a different approach here, which will be assuming the characteristic function as depending on the n without taking out the n and just making all the calculations that we have already done to show that in the limit, when n goes to infinity, all these terms with greater power in delta Q will go to 0. What the central limit theorem is saying to us is that when you have the systems that behave in the way statistical systems, it may be, for example, economic systems, maybe physical systems. But when we have systems that obey systems that obey the central limit theorem, the fact is that the averages, the mean values for the first statistical moment, goes to infinity as nm over n, and this just cancel out. And in fact, the variance also goes to n over n, cancels out. But the other moments, greater moments here, the kurtoses, the quartic moments, etc., goes to n with a larger number of n here, and then they cannot cancel out. And when you make the n go to infinity, n goes to infinity, you just get these higher moments to go to 0. This is the point here. Okay, we can make a more explicit connection with what we have done by taking again our characteristic function. Now I'm writing it with a capital letter, and also here with the capital Greek letter, the delta Q. Okay, so I'm assuming that I can use now here the delta Q. Again, I will have the same axiom, it doesn't change anything with respect to the axioms. We are, in fact, looking just at this integral here, which is a Fourier transform, and the axioms we are leaving exactly as they were. We are just assuming now that we can indeed make the expansion of the characteristic function. This is the expansion that we have made, okay, with respect to our probability amplitudes calculated in these points here. And when we made this, how should I say, this expansion, note that it is done up to second order, okay? I can write this term here. I won't show that, but you can show it yourself or look at the papers. This element here is just given by this one with the 4 here. But if you remember, this term here is just our how should I say that? Fluctuation, our fluctuation P, etc. So we may now make an expansion here. So let's write these as the usual term that we get. Let's assume that we have this. So we have here the variance. We should write this as delta Q squared over 2. And this minus 1/4 of this term. Of course, I will put the minus here and write this just as my sigma squared. Okay? But this is multiplied by this term here, which is connected. We know that this is just the average. Well, this is just the average in terms of delta Q. So, of course, I can expand this term to have delta Q squared over 2 sigma squared, and also 1 plus AM delta Q and another term here. In fact, this term here, the other term is, I have just an M squared, minus delta squared, and delta Q squared. Oh, okay, just that. So when I make the product, what I get is this expression. And here comes terms with a higher power of delta Q. But look at this expression here. Look at this expression here. This expression is exactly the same expression that we have found in the derivation of the Schrödinger equation. Of course, you may say, no, it was a little bit different, but it's different because I was there looking at the logarithm of the z, if you recall that. In here, I'm just writing the z itself. So when you took the logarithm of this expression, you get exactly the same expression that we have found in the derivation of the central limit theorem. Of course, each one of these variables are dependent of Q. Because of this, that slices that I am making on configuration space, okay? So when we do that, we get exactly the same expression, and we may say, I think that now I will have problems with these writings that I made here, but we may say that if you assume the central limit theorem and also this theorem here, or even if you just assume the central limit theorem to get into some expression of that, I'm saying that we are using here inverse engineering. I assume this the central limit, the theorem. I have this expression here, and then I will write this expression in terms of these elements. So what I get is this expression here for the characteristic function. And if I also assume that the system is governed by a Liouville equation, I get, of course, the Schrödinger equation, the derivation of the Schrödinger equation, because this derivation comes just from the equation for this variable here. So this, I think, shows the deep connection between the Schrödinger equation and the central limit theorem, and we learn from this connection that quantum mechanics is related to a random process of a very special kind, those which is Gaussian, those which to it applies the central limit theorem. As I will show you in the next class, the Liouville, the Langevin equation, when you make the interaction over the Liouville equations, these kinds of reasoning, this kind of reasoning that we used here in the central limit theorem will appear very clearly. We will show you the expression for the random variables and why these expressions go to this or that limits and etc. explicitly. And you will see why this Langevin equation goes to the Schrödinger equation in the limit of infinite number of random variables, random steps. Okay, so this is what I would like to show to pay my debt to you. And now let us recollect some of the results that we have obtained. We have made a very large number. We have derived a very large number of results. I will put them here in very simple and summary, making just a summary of the results. So our first derivation was the characteristic function derivation. With this characteristic function derivation, we have shown from where it appears, what is the origin of the operator structure of quantum mechanics, because we know that the characteristic function induces on the problem an operator structure. This is why we use a characteristic function after all. We have then connected this approach with the Feynman's path integral. And we have then have some hint that our quantum mechanical problem should be connected to fluctuations. We then have searched for a justification for that, because our process here is to assume something only if you have a mathematical structure that gives you support to assume what we are willing to assume. So we have made stochastic, an entropy derivation of quantum mechanics. I will put the derivations like this, because they are enlightening us. Sorry. So we have three derivations here. Of course, this is not my derivation, but I'm assuming that since I made the connection between this derivation and mine, of course, I can assume it as participating in the overall derivation of quantum mechanics, okay, which I am using. So I have made this connection here. Since there is a connection here, everything is connected to one another, even if this connection is not very easy to see, okay? This one is much more easy to see, because the symbols here are very close to the symbols here, because here we use Lagrangian physics and here we use Hamiltonian physics. From this one, we have seen that we may assume derive, in fact, the Bose-Sommerfeld rules only for the situations in which we have symmetry. So we have connected Bose-Sommerfeld rule with symmetry. And we have seen that by making such a connection, we may explain most of the wave-like experiment. I will say all the wave-like experiments, but of course, let's say at least some of them, the most important ones that we know of, the wave-like experiments, just in terms of particles. Of course, particles, symmetry, and discrete momentum exchange. Okay. Okay. So there has to be some parenthesis here. Okay. So continuing our search for more elements to interpret quantum mechanics, we have made this one. Gives us the hint, the perception that quantum mechanics should have something to do with random movement, because we may have fluctuations without random movement, okay? You may have, for instance, mean square displacement, etc., without having random movement. The random structure of your theory can come from for instance, the shock, the collision between molecules in a gas, and the molecules themselves are flying, are performing classical trajectories which have no random behavior itself, randomness itself. So in this case, we have a guess that this situation should be related with random behavior. But we have not, at this point, proved that this random behavior actually exists in the realm of quantum mechanics. Then we have made an stochastic derivation. We have, in fact, used a stochastic derivation of the Laplacian settle. Again, an enlightening part of our process. In this stochastic demonstration, we have seen that the stochastic velocity should be connected, for instance, with the gradient of the logarithm of ρ, with some constants here. And in fact, the variance is given by the divergence of this stochastic velocity. And then now we are sure that random behavior is okay. Because of that, we are sure that fluctuations are okay. Because of that, we are sure that the interpretation in terms of particles, exchange of quantized momentum and symmetry are okay. And now we have seen that we have used in all these approaches the assumption that the expansion can be up to second order. We have doubt about that. Each situation here is showing, is removing some sort of doubt. The doubt here is the expansion up to second order. Let me write this one. And we have thus made the connection with the central limit theorem, which removed this problem. This is also a derivation because of what I have just said. And with this derivation, which we are connecting, mathematically connecting all these derivations, we have just connected this derivation to the characteristic function derivation. So we have removed the problem of second order, so that second order becomes just okay. What I'm doing what I'm doing here, and I have written this diagram here without knowing, but just to, I think I see it now, to show you that I'm trapping you. I'm trying to trap you and leave for you no space to release yourself. Because at each point, I'm presenting the problems of the approach, and in the next step, I'm just removing this problem of the approach. At the end, you, of course, this is my hope, I hope that you will find very difficult to get rid of this trap that I'm building to you. So be careful with me. Okay. But the fact is that in this process here, with now the constructs, all the constructs that we have so far obtained, which are fluctuation, which are random behavior, which are averages, which are local temperatures. I didn't talk about this construct here, but it appears in the course of derivation, because of course we have systems which are random, and if systems are random, of course this is connected to temperature, and since this is given in terms of x, we can show that this thing here is related to a local temperature. Okay, and we have a number of other constructs that come from the process of derivation, and also the assumption, because of the axioms, this one, that quantum mechanics is primarily related to ensemble. Okay, but now with these results here, I can guess. Note that I'm writing an arrow here again with an interrogation mark. I can assume, at least I have a hint, that there must be here, or there at least maybe here, a connection with single systems, because I will assume that the ergodic principle can take place for at least some situations that will connect ensemble to single systems. If the ergodic principle is correct, I have talked about that in the last class, we will have two time structures to interpret quantum phenomena. One, which is always valid, which is the ensemble one, and it's always valid because of the sort of derivation that we have made, and one for a single systems, which depend on a time window. And these two may be connected and be assumed for some systems in which the ergodic principle applies, but with an enormous amount of caution, because as I showed it to you, sorry, when you try to force a single system interpretation where just an ensemble interpretation is appropriate, which is in those experiments where you have destruction of the initial system, the system is not allowed to return to its original situation, so you can't continue to make averages in the necessary time window. So it's not possible to interpret the problem in the single system approach. And if you try to force this interpretation, what you get is just the paradoxes that you find in the realm of quantum mechanics. For instance, the paradox of the Schrödinger cat, which is very easily understandable if you assume an ensemble interpretation and argue that single system approach is not available for that system because of the way we have done that. In spite of killing the poor cat, if you just make them sick, of course, with sickness that can be reverted, you can apply a single system interpretation for it. But you will have to wait a very large number of time, a very large amount of time, for the cat to be good again, and the vessel of that disposes the venom, that releases the venom, will be, of course, possible to release it again, so that the cat can become sick again. For instance, we can leave some coronavirus for the cats, and wait that they are better again, so we can continue to make it. But what is the difference between these two situations, the Schrödinger cat experiment and the Olavo sick cat experiment? The Olavo sick cat experiment just doesn't kill the cat. This is the notion of destructive experimentation. Okay, we have seen that this is the same with the two-slit experiment. The two-slit experiment gives us very strange results if we try to assume that it applies to a single system, when we assume that the problem must be interpreted, the physical situation must be interpreted in terms of ensemble, we just get a very usual and obvious situation if, of course, we assume together with ensemble discrete momentum transfer between the incoming particles, and the screen with the two slits, or one slit, if you will, doesn't matter. In one you will have diffraction, in the other you will have interference, and you can show this mathematically. Okay. Then we have doing by means of this amount of results, we have argued that quantum mechanics should be, because of these relations here, should be seen as a theory assessing an ontological realm, which in this approach is corpuscular. I don't know where it is here, which is corpuscular. So we are talking about a corpuscular nature. But quantum mechanics also is also related to behavior, the behavior of the system. And the behavior of the system, which is random, I will show by simulations to you next class, tomorrow, that the behavior of particles, of corpuscles, can, in a time window, just recompose, just rebuild a wave, a usual wave of quantum mechanics. If you watch the videos of this part, which is the one that I will be presenting tomorrow, you will see in the videos the simulations. I will try to make them using the app that I have just done, but you can see that in the videos too. Okay, so what I have said is that if you assume the possibility of these two levels of descriptions, this is an ontological level of description, this is what I call an epistemological level of description. This is ontological. You have no duality, you have no need for talking about duality anymore. And I think that this is now a belief of mine, that duality is the central element of the usual approach to quantum mechanics. If you get rid of duality, and of course complementarity, because we are not linguists, you may interpret quantum mechanics in very, very usual terms, because quantum mechanics becomes just a random system with, of course, very specific ways of presenting its randomness, which is by means of structured fluctuations, which are the signatures of the states in some quantum system. And so that what quantum mechanics really gives us is exactly this universality class, because it's connected to central limit theorem. in which we have not only the expression for the fluctuations, but also a number of other really important results. And I have made the relation, which is what I was searching from the beginning of the presentations, the classes, the reference, not the references, referents, são os referents of this symbol, of the theory, and the reference of this symbol are the particles, and the referent of this symbol is the behavior. Just in the very symbol of quantum mechanics, the main symbol of quantum mechanics, we have exactly these two levels of description. And when you try to collapse these two levels, which is in fact duality, it is when you try to do that the paradoxes begin to appear. Okay? Without that, quantum mechanics can be explained with no paradox in any sense. No paradox whatsoever. Okay, so we have made these three developments here, and in the next class I will show you the last derivation of quantum mechanics, which will be the last, let me put it here, the last little sum here, which is the Langevin equation of quantum mechanics. And the beautiful of this interpretation is that it connects this derivation, which is the central limit 1, with it's another way to connect the central limit theorem to the characteristic function theorem, but now showing what are exactly the random variables that appear here. Here in this derivation, I will make explicit the random variables that was just presented in an abstract way in the central limit theorem. And I hope that in this situation, you and we will have a very concise and consistent and free of weirdness interpretation of quantum mechanics. We are here touching a very important element of physics, modern physics, which is, let me do some bad philosophy here, okay? Just for a moment. Give me the freedom to make this. We are living in a century, more than a century now, in which reason is into question. For a classical, for the classical zeitgeist, reason in the realm of physics at least is assumed to have a direct, or at least an indirect, but good connection to nature. In the sense that in such an approach, such a vision of the world, a world picture, if you have a theory, whichever theory you may want, which gives something that reason cannot grasp, so you are probably with the wrong theory. Nowadays, we are in a situation in which we have the inversion of that. I know that many of you are suspicious about the things that I'm trying to show you here. And this is just because you were born, intellectually speaking, within a perception of the world in which reason is now assumed to have barriers to relate itself to nature. And not only nature, in a number of other approaches to other situations, for instance, in anthropology, for instance, in psychology and other situations, you also have this kind of barrier being assumed between reason and the nature that is, of course, the object of these approaches. So in the realm of physics, one of the barriers that we find is just the complementarity principle. Complementarity principle says exactly that our reason, which was built within our macroscopic existence, cannot grasp, cannot take hold of the microscopic behavior of nature. And as I have said, this is not a physical axiom. This is not a physical principle. It is a linguistic principle that is used just to uphold, to make it acceptable, the duality principle. If you don't do that, this becomes just pure absurd. So what this makes, and it appeared in one of our presentations, not my presentation, but the first presentation of this school, efforts, is that this kind of perception of the world, of worldview, when it creates barriers between reason, with our reason capabilities and nature, is that you become very suspicious of what reason can bring you. And in fact, nowadays I'm showing you an interpretation of quantum mechanics. Sorry, that has no kind of weirdness whatsoever. I know that many of you are just saying, well, if this approach has no weirdness is estranheza, tá? If this approach has no weirdness, probably it's wrong. Do you understand the difference here? How you? It's exactly the opposite situation from the usual one, the zeitgeist of the Illuminist approach. And this kind of release of the connection between reason and nature, this is my conclusion. I'm doing here a personal statement. It is the reason, is on the foundations of what we are looking at, the uses and in fact misuses of quantum mechanics as some sort of basis of everything. Anyone here, anyone now in the world may seem to understand quantum mechanics and talk about it in the psychology, quantum psychology, quantum administration. I'm not being I'm not making a joke. This is actually what you can find in the internet, for instance. Quantum psychology, quantum administration, quantum engineering, quantum physics education, quantum whatever you want to. And of course, you have those people which are, I don't know the name in English, esqueci até em português, which try to give you advices for a better life, of course, and almost all of them talk about some quantum mechanics thing. But you can't criticize these people without turning your criticism to yourself and looking of what kinds of things we are talking about in quantum mechanics. We are talking about many worlds. We are saying that quantum mechanics is pointing to a possible existence of multiverses. And so when you see those people saying about quantum psychology, let me be quite honest with you. I believe more in quantum psychology than in a multitude of universes. And worse, a multitude of universes that cannot be accessed by any kind of experiment whatsoever. Look that in this theory, we by not having duality, we do not need a complementarity principle. And in fact, obviously, we don't need the notion of observer. The notion of observer is just a notion that you need when you are doing an extrinsic interpretation of quantum mechanics. And I have already said and showed to you that this interpretation is an intrinsic one. And it is intrinsic because it assumes that those fluctuations are indeed the signature of the quantum mechanical system that you are assuming at in some concrete situation. It has nothing to do with possible interventions of observers into quantum mechanics. And I note, of course, a very important element here with regard to observers, that the variables of the observers are never made explicit in the Schrödinger equation. The Schrödinger equation is just something like that. And of course, you don't have here, let's put here, this one to be simple. You don't have here any variable that refers to an observer. And this is why the interpretation based on observer can find almost any explanation for a quantum system. Because since the observer is not constrained by the appearance of the variable here, which will change the results, in fact, the mathematical results, you can make whatever you want with the observer without changing your target theory. In fact, Popper has criticized not psychology. Freud is psychoanalysis. Popper has criticized psychoanalysis just by saying that whatever you want to say for a psychanalyst, he will say that this is due to your previous history of life. And so he can explain everything, because you can get control of what this history is really means. And Popper has criticized the Marxism too, because for him at least, wherever thing you show that is not connected to Marxism, the Marxists can encompass this result and show that in fact Marxism is correct because it explains what you are just saying. So Popper was very critical with respect to these two approaches, and he was in fact very critical to quantum mechanics itself for the same reasons, besides others, that I say to you in this exposition. So this is what I would have to say to you today, but be sure that tomorrow everything that I have said here will be shown by means of experiments. Of course, simulations, I'm assuming simulations as a type of experiment, computerized experiment. So I will show you the difference between behavior in nature by simulated Langevin equation. Of course, this Langevin equation will give us a structure, fluctuation structure, which is connected to this situation here, of course, because of the mathematical connection. And I will also show you the appearance of the ergodic hypothesis. I will show you that when you make ensemble simulations and when you make single system simulations, you get the same result. This is what I would like to say. Let's try to get into the last day. I'm exhausted, but tomorrow will be easier because I will just derive the Schrödinger equation using the Langevin equation, and then we will just see simulations, and let us do that to they give a finishing, a completion of this approach. Thank you very much for watching me. Well, now, as usual, I am open to answer to your questions, whatever questions you may have. I'm just trying to get out of here. Okay, now. Okay. Okay. And let me stop showing. Okay, I am now open to your questions. Of course, you have, if you have. Let me see if there is any question to answer. Okay. Yes, Manuela. Manuela is asking that if it's possible to demonstrate the central limit theorem using another method instead of the Fourier transform. Yes, there is a number of methods. This one using the Fourier transform was done by Lévy, a French mathematician. And I use it, of course, because it is easily connected to what I have done in the characteristic function demonstration. Okay, but yes, there are a number of possible demonstrations of the central limit theorem. Virgulas is wants to understand what happened with the Schrödinger cat. I will give you a brief explanation of that, virgulas. because I have already done that before, but of course I can do that again. Let me just give you here, I will choose here a window. And the explanation for the Schrödinger cat, but well, bear in your mind that we are here assuming the possibility of connecting an ensemble. Oh my God, ensemble interpretation of physical situations and single system interpretation. Okay. So in the Schrödinger cat situation, you have a box. In this box, you have a cat. Let me do here a simple cat. And you also have a device that can, in some way, by means of a random behavior, release venom, so that if this device releases the venom, of course, acts on the cat, and the cat dies. And if this element here does not release the venom, the cat doesn't die. So you have a 50-50, we are assuming here, a 50-50% of the venom to be released, because this is the behavior of this instrument, this apparatus. And when you come to represent this in quantum mechanics, you say that the probability amplitude related to this problem is just the sum of this probability density related to death and the cat here, and the superposition, of course, of this probability amplitude here related to the live cat. And this is in this way of interpreting the problem, look that I am portraying the problem in a way that I am assuming that we have a single system. And if you have a single system and you believe that these two representations are correct and related to the single system, of course, you have a superposition of two states at the same time, two states, because the time here appears in all the expressions at the same time, of course. And you are assuming here that you have a dead and alive cat. And this, of course, since the cat is a macroscopic system, this is what Schrödinger pointed as a paradox, because a macroscopic system should be in one state or exclusive or the other. Okay. But what we have showed in our approach in this present interpretation is that the relation between the ensemble and the single system one are not that easy. So have ensemble, we have single system. And we have shown that this connection can be done only if you may apply the ergodic principle. Thus, average is made upon a single time, an instant of time, can be connected to the averages made on a time window. But of course, for this principle to apply, you have some positions, you have some conditions. And the condition, of course, is that the system is not destroyed. The system cannot be destroyed. Because if the system is destroyed, of course, what you will get is the breakdown of the possibility of making a single system approach. Because you need, and this is the important thing here, the time structure of these two possibilities. You need a time interval to make the interventions in the system, to measure the system in a way that you can connect this approach to this one here. But if the system at some point is destroyed, you can continue to make the single system approach. You can continue to make the averages, so the experimental measurements, and so you won't be able to make this connection here. And in fact, if you look at this problem with more cautious, in a more cautious way, you can see that this is a time-dependent problem. This can never be constant here, independent of time, because if there is a 50% situation in time t equal to 0, if you expect, if you await 100 years, after you open the boxes, you will find all the cats dead. All the cats will be dead. So the probabilities of finding a cat alive or dead will change with respect to time. And this is why there is a difference between the time structure based on a single system and the time structure based on an ensemble. From the point of view of an ensemble, what you really have is not a single system with one single cat and one venom vessel, etc., etc. What you have, and I will not draw the cat here. What you have here is a number of identically prepared cat systems. I will draw. It's too nice to draw the cat. So you have a number of cat systems, and in identical situations. And now, oh, come on. Forget about that. And now you may make an intervention, an experimental intervention in the system at some instant of time t. And what you are measuring is the cat in this system, the cat in this system, the cat in this system, the cat in this system. So the interpretation of this probability amplitude here, which is time dependent, dead and C2 alive, is completely different, because now what you're saying that at some instant of time, remember the time structure of the theory, at some instant of time, when you measure each one of these identically prepared systems, because of the randomness of the apparatus that release the venom, you will find a number of systems with cats dead and another number of systems with cats alive. But there is no superposition of these two situations. You don't have cats dead and alive. You have some cats dead and another cats alive. And in fact, the time evolution of this system is such, as I have said, that after some very long time interval, you will have this situation with just dead cats. That is, these alive cats will go to 0 in some sort of ways like this. okay? And you will have at the end just this situation here, which will be something like that when normalized this goes to 0, okay? So this is the difference between the two approaches, and this is connected, of course, with the time structure of the interpretation that you are using. If you use in this problem an interpretation that assumes that you may have whatever time interval you may want to, of course, we will go into a number of difficulties and paradoxes, because of course this is not the situation. You cannot do that, okay? Okay, this is how the Schrödinger cat is understood in the present approach. And as you have seen, when you assume that ensemble and single system play some role, some connection between them, but you are cautious about the use of this connection because it needs the ergodic principle to apply, you can you can get rid of the paradoxes of the theory. Okay, I hope I have answered your question. Okay, if we don't have any more questions, I think we can end and wait until tomorrow. If it is the cherry on the cake, we have this expression in Portuguese, a cereja do bolo, which will be the simulations that will show many of the things that I have said here. Okay, so I think we can end this class today. Thank you again for watching, and see you tomorrow.